In this video, we're going to do a few more examples of structural isomers, and we're going to focus on some examples with alkanes. So one of the examples I had told you to do was to draw all the structural isomers of pentane, C5, H12. And so we'll do that in just a little bit to see what you got. But I want you to notice that here we have some examples of several alkanes, from a 1-carbon alkane to a 10-carbon alkane. And take a look at what happens in the number of isomers as you increase the number of carbons. As you increase the number of carbons, you'll notice that you're also increasing up at a certain point the number of isomers or structural isomers that you have. And that's because you basically have more pieces to play with and connect in different ways. And so you can imagine that, this is with 10, it's just going to get larger and larger and larger as you go. There are formulas you can use to figure out how many isomers you have without having to draw them all. It's just not always consistent. They change based on how many carbons you have. So for example, if you were to try to figure out the number of isomers from carbons 1 to 7, you could use a formula, and you could probably figure it out yourself. I'll let you figure out maybe 8, 9, and 10, but you could use a formula which is 2 to the power of n minus 4, and then afterwards plus 1. So for example, let's say you have 5 carbons. Well, in that situation there, we do 2 to the power of 5 minus 1, or minus 4, sorry, plus 1, which is 2 to the power of 1 plus 1, we get 3. So we should have 3 structural isomers total. If your value that you get here is a negative value, you basically just omit that and you just do the plus 1. But that's only really valid up to 7 carbons. As soon as you have 8 carbons, 9 carbons, or 10 carbons, the formula changes a bit. So you can try it out and you can see if you could figure out what the formula is. I did link it in one of the documents. You'll see it next to the title somewhere up here in your document. That's basically this one over here. So take a look. You don't have to memorize those formulas. They can be helpful for some multiple choice if you want a quick answer to things. But really the most important skill is that you're able to identify structural isomers and draw some. Chances are you won't be asked to do 75 structural isomers on a test, but you could be asked, here's decane, draw 3 structural isomers or 4 structural isomers, for example. And so for you, it might be good practice to try a few, especially the ones where there's 2, 3, 5, up to 9. And if you really want to challenge yourself for fun, you can try doing octane. If you want to do nonane and decane, go ahead and try that out. You'll get more practice naming the alkanes, but you don't need to. We're just going to focus on a few. We'll do the C5H12, and we'll actually do C4H10 as well, just to show you how limited it can get when you have fewer carbons. So we'll start with the C4H10. Remember, the strategy is to always look at what type of molecule you're dealing with first. This is a CnH2n plus 2 molecule. This basically means you have an alkane. That's the formula, right? Because you have Cn is 4, and then this H is 2 times 4, which is 8 plus 2, alkane. So we have a formula there. So we're dealing with just alkanes, single bonds, no cycloalkanes, no alkenes, no alkynes. Very straightforward. I like to start off with my first longest chain that I can make. So let's do that. And what I get is CH3, CH2, CH2, CH3. And so I have butane over here. And I think this is the longest chain I can get. That has 4 carbons in it, and it being butane, that's about it. After that, I'm going to try to make the second longest chain. So I'll try to make a chain with a branch in it this time and see if that's possible. So I'll do 3 carbons. I usually shorten it by 1 every time. And then I'll put a carbon over here as a chain. CH3, H3, H, H3. I want to check to make sure it's the proper formula. So here I had C4, H10. Here I want to name it as well. So this is 2-methyl propane, which is C4H10. Has the same number of carbons and hydrogens. Great. So I do want to show you a common pitfall students do. So they'll say, okay, well, let me try to move this around to get another isomer. So they'll say, I'm going to take this and place it on this carbon over here. And so they'll go CH3, CH2, CH3, and they place that little branch over here, and they'll say, here's another isomer. And they'll think this is another isomer made because it has C4H10. But what you'll notice is this is not a new isomer from the ones you did above. This is actually just butane. This is just butane with this bond over here just facing down now. But it's still just 1, 2, 3, 4, no branching. This is part of the main chain because it's at the terminal carbon there. This is simply butane. So this is not an extra isomer. So just, I think at this point, if we move this carbon anywhere else, we're just going to make butane again. So that's basically it. There's nothing else we can do. You can't really make a 2-carbon chain. If we try to make a 2-carbon chain, you get this. You go, oh, let me try to do 2 carbons like this and make these branches over here. Those aren't branches. This is butane at this point. We can't do that. And you can't make cyclobutane because cyclobutane doesn't have that formula. Cyclobutane, if you tried that, you'd get CH2, 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 connect, CH2. This is C4H8. This does not share C4H10. So I'm just showing you some common pitfalls students make. That's why I try to see what type of molecule I have at the beginning. It's an alkane, not a cycloalkane, not an alkene or an alkyne. And it helps me to determine what I can and cannot make with that formula. And so I think butane, or this C4H10, can only have really 2 isomers, 2 structural isomers, and that's going to be the butane and the 2-methylpropane. So let's try another one. Let's try the C5H12 and see how many we can get. So C5H12, once again, is one that follows the CnH2n plus 2 formula. In other words, it is an alkane. And so since we have an alkane over here, there's only going to be single bonds. And we can't do cycloalkanes either because, again, cycloalkanes have a different formula altogether. So let's start off with the longest chain. And this time we'll do some line diagrams for fun here. So 1, 2, 3, 4, 5. This is the longest chain with 5 carbons that we can get over here. So 1, 2, 3, 4, 5. And this would simply be pentane. I'm then going to try and do another chain that's a bit shorter. So I'll reduce it by 1 and just put a branch somewhere. So 1, 2, 3, 4, and I'll put a branch here. And if I do that, I get 2-methyl butane. This is an isomer, a structural isomer of pentane, of C5H12, since it is C5H12 if you count all the carbons and hydrogens. If you have trouble counting the number of hydrogens in the line diagram structure, just do the condensed structure and that should be fine. C5H12. Again, I'm going to show you a common pitfall students will do. They'll continue with this and say, great, I'm on a roll here. Let me draw the same structure here as before, and I'm just going to move our substituent over here. And when they do that, they'll say, I'll get 1, 2, 3, 4, 3-methyl butane. But that's actually wrong. That's not 3. We have to start counting this way now because that will give us our lowest substituent. So this is simply still 2-methyl butane. So that's not an extra isomer. It looks like since we can't really move that substituent around anymore, we are essentially done with that particular setup there. So we can't really move the substituent around anymore. If it was a longer chain, we'd likely be able to move it around some more. Like if it was a C6H14, we could probably move it around a bit more. And you can try that out yourself. There's only 5 isomers for hexane, so you can try to get that. But let's, and if you want to check your work for the hexane isomers, you can just always look it up on Google after you're done to see if you got the right ones. But it's a good challenge to try hexane after you do this. So now I'm going to try another strategy. I'm going to see if I can get another isomer of pentane. It looks like, let's see if I can make a shorter chain at this point. If I can maybe make a propane chain and perhaps see if I can get another branch like that. Does that work? Let's see. So if I do that, try to name that molecule. If you do this, you'll see that you have, actually, this is the same one as above here, just rotated. So that one won't work. Let me try to make it instead like this, because notice that I just made the same one there. Sometimes a mistake happens. Let's try to make a 3-carbon chain there. I'm going to put a substituent here and a substituent there. I think that'll work because that gives me 1, 2, 3 carbons as the longest chain. Whatever direction I go, it just gives me 3 carbons. So that works, actually. So here I get a 2,2-dimethyl propane. And that gives me the formula C5H12. Just in case you're not sure, don't forget there's 3 carbons, there's 3 hydrogens here, 3 hydrogens here, 3 hydrogens here, 3 hydrogens here, 0 here, because that carbon's connected to all the different carbons, 4 of them. So that's 4 hydrogens. And then there's 1 carbon. This is 2 carbons. This is 3 carbons. This is 4 carbons. This is 5 carbons. So that would be the C5H12. And I think that's all we can do. There's no other strategy to moving this around. You can try redrawing it in different ways. You can try model kits, and you'll see that there's no other ways to really reconnect this without repeating the isomers we already have. So we have 3 different structural isomers for the C5H12 formula: pentane, 2-methylbutane, 2,2-dimethylpropane. I'd recommend you try hexane, see if you can get all 5. It's a good challenge, and even if you want to try heptane as well. Don't forget, check the formula first, see what it is, an alkane, alkene, alkyne, or whatever else you're given. And at the end, when you're done drawing, make sure you name and you verify that it has the same formula as what you're supposed to have. So the reason I do the naming is because it helps me to see if I accidentally duplicated a molecule. So if you name it and you go, oh, this is the same molecule because I see it has the same name as something else I named above, then you know you made a mistake and you're done with that length, for example. So those are some strategies you'll develop going forward.